Now we can start.
So, good afternoon, everyone. I am Ashutosh Singh from RRI, and I'll be talking about our theoretical and experimental investigations towards the creation, characterization, and manipulation of quantum entanglement in a photonic system. This is the brief outline of my talk. So, basically, what I will be talking today is the static and dynamic properties of quantum entanglement. So, how different entanglement measures compare with each other in the context of two qubit states, and given a two qubit state, how does it evolve in a noisy environment? And what we'll see is that entangled states decohere. So we'll propose a scheme to protect entanglement from decoherence. So, towards a comparison of entanglement measure, what we'll find is there is intriguing nuances between different entanglement measures, and we'll specifically see that entangled state undergo what is known as entanglement surrender. And because entanglement is a very important resource in quantum information processing protocol, therefore its longevity is important for accomplishing any of the quantum information processing tasks. Therefore, any scheme which actually protects entanglement from decoherence and prolongs its lifetime will be helpful in accomplishing any of the aforementioned tasks. So to begin with, what I'll be talking about creation of quantum entanglement. So what basically we do is we use the process of spontaneous parametric down conversion to create a polarization entangled photon source. So basically we shine an intense laser beam onto a nonlinear crystal, wherein one high energy photon gets absorbed in nonlinear crystal and two lower energy photons gets created, satisfying energy and momentum conservation. So this is energy conservation equation, and this is momentum conservation equation known as phase matching condition. And they come out in the form of a cone as you see here, and then this cross section will be basically a circle, and we couple photons from diametrically opposite positions, and which will be correlated in polarization energy time depending on the way we design it. So this is the schematic of our polarization entangled photon source. Basically, we have a laser beam, and then we use half a plate P-base combination to correct for the polarization, and then we use a half a plate to convert the horizontally polarized laser beam into a diagonally polarized laser beam. And then what happens is that when this beam passes through a nonlinear crystal, there will be temporal delay between the horizontal and vertical polarizations. To compensate for that, we use the temporal compensator, and then these photons go in the form of a nonlinear, go in the form of a cone, and we couple photons from here and here diametrically opposite positions. And what you see here is quarter plate, half a plate, and P-base combination. This is used for quantum state tomography. Photons are filtered through narrow bandpass filter and then sent through a single mode fiber to detectors, and then there's a time tagging module which does the coincidence measurement. So this is basic setup of a polarization entangled photon source and quantum state tomography for its characterization. What we do is basically we prepare a maximally entangled state, Bell state HH plus V well root 2, and what we find is that the state that we obtained in our lab had a purity of 96.57% and fidelity of 97.85%. And what you see here is real and imaginary parts of the density matrix of 2-qubit entangled state. Then we went on to quantifying quantum entanglement, and what we see is we compute different entanglement measures, negativity, entanglement formation, concurrence, log negativity. So we see that negativity gives a value of 0.645, entanglement formation gives 0.95, concurrence 0.9652, and log negativity 0.9741. But what we observe is that for the non-maximally entangled state, and of course experimentally the state that we will prepare will never be a perfect Bell state or perfectly entangled state. There will be some imperfection in the experiment, and therefore we'll be getting only non-maximally entangled states. But what happens is that the quantifier that we use for quantifying entanglement gives significant departure in terms of quantifying to what extent the state is entangled. However, for maximally entangled state, all the entanglement measures agree that the value will be 1. So at this point, we started looking into a comparison between different entanglement measures. So to study this theoretically, what we consider is that we consider 2-qubit pure state psi equal to C000 plus C111 written in Schmidt decomposition form. And then we theoretically compute all the entanglement measures, namely concurrence, negativity, log negativity, entanglement formation, and entanglement entropy. What you can see from this graph is that concurrence and twice negativity match with each other, and entanglement of formation and entanglement entropy match. Log negativity, concurrence, and entanglement formation are three distinct entanglement measures that we'll use for the further study. This is the expression of these two entanglement measures, and then we started defining the deviation of a given state from maximally entangled state, meaning that if we have a non-maximally entangled state, say its entanglement measure is say EM, then how much it is away from a maximally entangled state whose entanglement measure will be 1. I mean, any of the entanglement measures will give a value 1. So how far it is from the maximally entangled state. So to quantify that, we define this quantity Qn, Ql, and Qe. These are normalized quantity which varies from the range 0 to 1, 1 being from the separate state and 0 being for the maximally entangled state. Then we define suitable differences between these Q parameters, and this is basically absolute difference between the deviation parameters Q and QL and QE, and these are delta QNL, delta QEL, and delta QNA. What we immediately see is that as we vary the Schmidt coefficient C0 for a value close to 0.21, there is a significant departure between delta Q parameters. And theoretical estimates show that the maximum value of delta QNL, meaning that entanglement measure defined by negativity and log negativity, gives a difference of 8.6% for a value of C0 equal to 0.227. And negativity and entanglement of formation gives a difference of 14.99%, and entanglement of formation log negativity give a difference of 23.57%. What is interesting to see that while these entanglement measures are defined differently, so one may assume that okay, because they're defined differently, therefore they will give different quantifications of the entanglement. But then we also observe that negativity and concurrence, twice negativity and concurrence, actually match exactly with each other. So, and also on a scale of 0 to 1, the difference could be as high as 23.57%. So while this was known fact that they are defined differently and therefore they could show some departure with each other, but then this maximum deviation between the two parameters could be as high as this was slightly surprising to us. Then we went on to preparing these states experimentally in the lab, and we prepared 3 different states, and different parameters of these states are given here. Negativity, purity, log negativity, entanglement of formation, and all these Q parameters. And what we see is that for the state 3, their delta Q parameters are close to the maximum value that we just saw here. I mean, like 8.6%, 15%, and 23%. So we got the values very close to the theoretical estimates from the numerical optimization. Then we moved on to extending this analysis to higher dimensional systems. In particular, we considered bipartite qubit states and tripartite qubit state. And what we see is that these entanglement measures may not be monotonic with respect to each other. What we see in the case of 2-qubit pure state is that the entanglement measures that we saw earlier remain monotonic with respect to each other, but that condition does not satisfy anymore in the higher dimensional systems. For bipartite qubit state of this kind, C000 plus C111 plus C222, the maximum deviation between negativity and generalized concurrence can be as large as 36.6%. And for tripartite pure qubit state of this kind, there are 2 different entanglement measures called tangle, and there's a global measure of entanglement. While they're defined differently, but for this particular state, they turn out to be the same, and therefore the delta Q values will be 0. So through this study, what we find is that while entanglement measures in two qubit closed states, they remain monotonic with respect to each other, but their quantification could be as high as 23.5%. But in the case of high dimensional systems, not only they do not remain they do not remain monotonic, but their differences could be as high as 36.6%. And on the other hand, there could be another measure of entanglement for which they could exactly match. So there are significant what to say nuances between different entanglement measures in the context of qubit and high dimensional systems, and therefore I mean, the question that we ask is, should there exist a fundamental criterion for any preferred measure of entanglement, or should the measures of entanglement be defined in the operational context? Then we went on to looking some further directions, and we defined measures based on fidelity and Frobenius norm. So C is a measure based on fidelity as given by this equation. And then another measure called D is defined based on Frobenius norm, which is given by square root of trace of A dagger A. And when we compare fractional deviation parameters corresponding to C and D with earlier defined entanglement measures, what we see is that C and D are exactly equal. Again here, C and D are defined differently, but D and C are exactly the same for this choice of state, and it gives an upper bound to N and Ln, but not for the entanglement of formation. Then we moved on to defining another deviation parameter based on Bell violation. So for any two qubit entanglement state in two setting two outcome scenario, we have Bell violation given by this expression, and the fractional deviation parameter is defined by maximum value of Bell violation that a maximally entangled state gives minus the violation that a non-maximally entangled state gives normalized by the maximum value. So when we compare with again earlier defined Q parameters, what we find is that this QPV gives an upper bound to all the three earlier defined entanglement measures. So this is the direction that we explored towards the study, and this completes the first part of my talk. If anyone has any question so far, then I can take it up. Okay, perhaps I should proceed then?
Yes, you can proceed.
Okay, thanks. So in the second part, I'll talk about entanglement dynamics in a noisy environment. We consider a quantum map of a qubit which is present in an amplitude damping channel. So if we label the system states as G and E and the reservoir states as 0 and 1, then if the qubit is in the ground state and the reservoir is in the vacuum state, there is no excitation to exchange, and therefore they will remain there. If our system is in excited state and the reservoir is in the ground state, then there's a probability 1 minus p that they will remain there, and there's a probability p that the system will de-excite to the ground state, and there'll be one excitation in the reservoir. And this p is given by 1 minus exponential minus gamma t under bar Markov approximation. If we extend this analysis for a 2 qubit entangled state, do this and then write the complete unitary evolution for system and environment and trace out the degrees of freedom of the environment, then what we find is that for initial state of this kind, the concurrence for two cases when parameter A is 0 or 1 is exactly the same, that is 0.67. What happens is that the state which has A equal to 0 undergoes complete asymptotic decay of entanglement, meaning that there is always infinitesimal amount of entanglement present in the system. till t tending to infinity. Whereas in the other case, when a equal to 1, the system gets disentangled at a value gamma t equal to 0.5. So this state with a equal to 1 becomes useless for any of the quantum information processing task. So the idea is to come up with a scheme where if we have a state of this kind with value a equal to 1, then can we protect entanglement beyond this 0.5? For this matter, we have given an experimental proposal for a photonic system wherein we use pollution entangled photon source and then study entanglement dynamics in a noisy environment where amplitude damping channel is mimicked using a set of half-wave plates, and then output modes of this interferometer, which are A and B, basically mimics the modes of the reservoir, and when they're traced out at this point, it basically acts as amplitude damping channel. So what happens is that when you have a horizontal polarization photon getting into the interferometer, it will get transmitted, come this way, and then get transmitted to mode E. Whereas a vertically polarized photon will get reflected. There's a half operated angle theta, which will convert the vertically polarized photon to cos 2 theta v plus sin 2 theta h. And then this will come here, and then part of the component will go to mode A, and then the horizontal component go to mode B. And when these two modes get recombined at this PBS incoherently, then it basically acts as an amplitude damping channel. Same discussion applied for the for this interferometer as well. So basically, we send two photons into two different displaced Sennett interferometers, and then mimic amplitude damping channel using these half the plates, and then we recombine the polarization components at this PBS incoherently, and then this does the complete ADC mimicking. So the quantum map for such a system is given by this. A horizontal polarized photon would go to mode A. A vertical polarized photon in the presence of a half a plate theta will partly go to mode A, and then horizontal component will go to mode B. And if you compare this with the earlier shown ADC map, this one, there's a complete one-to-one analogy between the atomic system that we talked about here and the photonic system. So this analogy is used for demonstration of asymptotic decay of entanglement and then entanglement surrender. So we use this setup to show the ESD and AD. And what we find is that for an input state of the kind alpha HS plus beta VV, where mod alpha square is 4 times the mod beta square, then the initial state with concurrence close to 0.8 undergoes complete asymptotic decay of entanglement. So what you see here is a concurrence as a function of temperature parameter P, and the state remains entangled till P equal to 1. And the state purity basically comes to a minimum value of close to 0.8, and then again goes to 1. When both the qubits come down to ground state, again becomes completely pure, and therefore the purity comes down to a value here, and then goes back to equal to 1, purity equal to 1. So this is basically asymptotic decay of entanglement, where entanglement follows the usual asymptotic decay. On the other hand, if we prepare a state alpha HS plus beta VV with ratio alpha square equal to 4 times beta square, then this initial state again shares the same amount of entanglement, close to 0.8, but this initial state undergoes what is known as entanglement surrender. And this state completely gets disentangled at value P equal to 0.48. And then here purity basically comes down to close to 40% for this particular P parameter. And then this state becomes completely useless for any of the QIP tasks. Therefore, we come up with a proposal to protect entanglement for such a system. So the proposal is that suppose if we have a 2 qubit initial state, and then this entanglement state is, required to be sent through a noisy channel, which is impacted by amplitude damping channel. Then what we do basically is, in between we apply local unitary operation. Here, for 2 qubit case, we use NOT operations. And then suppose Charlie has prepared the initial entanglement state, and then he has to send the qubits to Alice and Bob. Then a priori, if we know that this state will get disentangled before they reach to Ellis and Bob, then it will be of no use. And to protect entanglement, what we do is basically we apply NOT operation in between, and then we compare the state uh, was which went uninterrupted through the noisy channel, and then the one which was suitably intervened using the NOT operation. So the what happens is that suppose initial state had of the form of this kind, then initial here we are plotting negativity as a function of again damping channel parameter gamma t. Then if initial state has a negativity of value 0.2, then if it would follow sudden death, and then state will get disentangled at value 0.55. But we apply local sigma x operation on both the qubits during the process of decoherence, and if you apply very early between 0 to 0.13 in this range, then this dynamics changes from this red curve to green curve, meaning that the state which was earlier getting disentangled at value 0.55 now undergoes complete asymptotic decay of entanglement, and it remains entangled till p tending to 1. On the other hand, if you apply NOT operation little later between gamma TB and gamma T8, the values are 0.13 and 0.28 approximately. So in this range, if you apply NOT operation, then the entanglement sudden death is actually delayed to a blue curve. So this initial disentanglement was happening across this line, but after the application of NOT operation, state gets disentangled around this curve. So we have been able to delay disentanglement from this point to this point, but it remains sudden death only. However, if you apply NOT operation much later, say between gamma T and gamma T, between 0.28 and 0.55, then what happens is that it actually speeds up the disentanglement process, and then state gets disentangled at a value of 0.48. So this gives us a recipe for entanglement protection. So we have a initial entangled state, and if we know the complete disentanglement dynamics, then we can find out what gamma TB, gamma T, and gamma T are, and then depending on our requirement, we can actually engineer the disentanglement dynamics. So by applying the NOT operation very early, we can completely avoid the ESD. By applying it little later, we can actually delay it, and by applying much later, we can actually hasten the process of ESD. So this proposal was transformed into an all-optical experimental setup as given here. This is similar to the setup that we saw earlier for ESD, but then here we have some added components for the manipulation. So again, we have a polarization entangled photon source. This goes through the display Sennec interferometer. There are some components for the path compensation such as P2C and others. So this photon traverses the interferometer in this direction, and then we apply a NOT operation. So basically, horizontal polarized photon goes through this way, and then NOT operation is applied, and then after the application of NOT operation, it becomes vertically polarized. So here, horizontally polarized photon plays the role of a ground state, and vertically polarized photon plays the role of excited state. So after it becomes vertically polarized, we apply amplitude damping channel using this half a plate, and then these go to different modes of the interferometer. Again, a vertically polarized photon goes this way because it is vertically polarized, meaning it is mimicking the excited state. Therefore, ADC amplitude damping channel is applied using half a plate H1, and then manipulation is done using half a plate H5. And then there are two components H and B. They split at this point P2, and then again half a plate H2 mimics the ADC, and then all the components go to different special modes of the interferometer. So the basic idea is to just mimic the proposal that I just showed here, that there is an initial entangled state, pass it through the damping channel, apply the NOT operation, and then again evolve in the damping channel. So using the analogy that we showed here, we have just extended this setup to accommodate the components which basically mimic ADC and then NOT operation, and then this is the complete setup for the manipulation. This experiment is currently underway, but I'll just show the theoretical results that we obtained. So if we have a state of this kind, alpha HS plus beta PV with mod beta square equal to 4 times mod alpha square, then initial entangled state was getting disentangled at value P equal to 0.5. And P and P prime basically show the ADC effect before the application of NOT operation and after the NOT operation, as we saw here. So this is basically P and this is P prime. Now what we see is that the uninterrupted system basically gets disentangled at value p equal to 0.5. But when we apply NOT operation on both the qubits, the system remains entangled till p tending to
Ashutosh,
1. Yes.
hello, you only have 5 minutes.
Yeah. I have just 2 slides. I'll wrap it up. So this state remains entangled in the earlier range of p parameter. Now what we see is that depending on the application of NOT operation, if applied very early, the initial state was getting disentangled at p equal to 0.5, remains entangled till p equal to 1 for the early range of NOT operation application. For the late range, we have this as a delay, and then when this blue curve dips below the red curve, we have hastening of ESD. This ESD manipulation experiment is currently ongoing, and we have the initial state fidelity of close to 90%. We are trying to improve it, and then we'll complete the manipulation experiment. So to conclude, what we have discussed is the preparation and characterization of Polish entangled photon source. What we observe is that towards quantification of entanglement, we find that different entanglement measures give different quantifications, and then they have significant departure from each other. We have studied entanglement dynamics in the noisy environment, and what we have found is that while two initial states which share same amount of initial entanglement may show different entanglement dynamics. One can undergo ESD and other can undergo ADE. ESD and ADE are experimentally demonstrated, and we have given a proposal for manipulation of ESD in 2-qubit system, and then manipulation experiment is underway. Thank you. I'm open for the questions.
So there are 2 questions, one
Yes.
from Aditi Sende. You can see it in the chat box. That's
Okay.
there. Can you see it, or shall I recite the questions? So I'll just recite what the questions are. Okay.
Can you just read
Yes.
it for me?
So the first question is from Aditi Sende.
Okay.
If you use SPCD2, can you improve the fidelity of the entangled states?
By doing what?
SPDC2, spontaneous parametric down conversion to.
It is a matter of using the proper source. Even with type 1 SPDC, we can get entangled states with high fidelity, just that we need to use lasers which have very narrow line width, and we have to do the proper temporal compensation. So it depends on the quality of laser that you use and how well the temporal delay is compensated.
Next
and type 1 and type 2 is just a matter of implementing SPDC, and either could be good or bad depending on how good the laser is and how well temporal delays are compensated.
So
does that answer
the next question is from
Thank you, Ashutosh.
Okay, ma'am.
Yeah, I have just one point, which is as an organizer.
Yeah.
In one of the slide, it is written that it is not for open circulation.
Yeah.
But you know that our entire thing is live streaming in YouTube, and it will remain in YouTube.
That's fine. I mean, it is just we just put it just to make sure that nobody.
That's just a clarification from us. I think we have already sent whether you have a consent or not, but just clarify.
Okay. Sure, ma'am. Yeah.
That's our next question. You can go, Shom.
Okay. So the next question is from Shilayat Kamal. He asked that, can you generate on tabletop JZ and W tripartite state? Could you please tell how the generation process differ for those two states, JZ and W states, tripartite?
For GZ state, we can use concatenated SPDC process. So here we have one SPDC, one SPDC setup where we have one photon splitting into two, and we can concatenate two of them to create the GAG state. For W state, maybe I'll have to take a look.
It seems that there are no further questions. Yes, there are no further questions. So let us all thank Ashutosh, and this concludes. Ashutosh, you can just unshare the screen.